Hello, and welcome to this presentation on the STM32C0 Reset and Clock Controller. The STM32C0 Reset and Clock Controller manages both system and peripheral clocks. STM32C0 devices feature 2 or 3 internal oscillators, depending on the device, and 2 oscillators for use with external crystals or resonators. Notably, there is no PLL in the STM32C0 series. Many peripherals have their own independent clocks. The RCC also manages various resets within the device. The STM32C0 RCC offers great flexibility in selecting clock sources, enabling designers to balance power consumption and accuracy requirements. The independent peripheral clocks allow power adjustments without affecting communication baud rates, and certain peripherals can remain active in low-power modes. Additionally, the RCC ensures safe and flexible reset management. Flexible and safe reset management, without needing external components, reduces application costs. The RCC manages 3 types of resets: system reset, power reset, and backup domain reset. Each peripheral also has its own reset control bits. The first type of reset is the system reset, which resets all registers except for the reset flags in the RCC control and status register 2. It does not affect the RTC domain. System reset sources include external reset via the NRST pin, a window or independent watchdog event, a software reset request, a low-power security reset, when stop, standby or shutdown mode is entered but prohibited by option bytes, an option byte loader reset, and brownout or power-on reset. The source of the reset can be identified using flags in the RCC control and status register. 2 option byte fields are used to configure the NRST pin: NRST mode, which selects the pin's mode, input-output reset, input-only reset, or GPIO, and IRHEN, which stands for Internal Reset Holder Enable. When IRHEN is enabled, the NRST pin is driven low until its voltage falls below the input low threshold. Upon power reset or wake up from shutdown mode, the NRST pin is initially configured as reset input-output and driven low until the option bytes are loaded, after which it is reconfigured. This slide shows a simplified block diagram of the system reset. All internal reset sources drive a reset signal on the NRST pin, which can also reset other components on the application board. No external reset circuitry is required, thanks to the internal glitch filter and power monitoring feature, which ensures a reset when VDD drops below the threshold. The internal pull-up resistor on the NRST pin is deactivated when an internal reset occurs to reduce power consumption. Additionally, all I/O pins, except for debug and test pins, enter analog mode during reset to prevent unnecessary power consumption before software initialization. The reset holder function ensures that NRST remains driven low until the voltage level of this signal drops below the input low threshold VIL, which is helpful when the NRST line has a large capacitive load. The second type of reset is the power reset. The brownout reset, BOR, resets all registers in the vCore power domain. When exiting standby mode, all registers powered by the regulator are reset. Upon exiting shutdown mode, a brownout reset is triggered. The third type of reset is the RTC domain reset, which affects the LSE oscillator, the RTC, and the RCC control and status register 1. Note that backup registers lie outside the V core domain. The RCC provides a wide range of clock sources to accommodate different power, accuracy, and performance requirements. STM32C0 devices incorporate 2 or 3 internal clock sources, 2 high-speed 48 MHz RC oscillators, HSI 48, with HSI USB 48 available only on STM32C071 devices, and a low-speed 32 kHz RC oscillator, LSI. Additionally, STM32C0 devices support 2 external oscillators for use with crystals or resonators. A high-speed external oscillator, HSE, ranging from 4 to 48 MHz, with clock security features, and a low-speed external 32.768 kHz oscillator, LSE, also with clock security. The I2SCKIN pin serves as a potential clock source for the I2S1 peripheral. While there is no PLL in STM32C0 devices, the HSI48 provides the maximum frequency and can be reduced with dividers. The system clock can be derived from the high-speed internal 48 MHz RC oscillator, HSI48, or the high-speed external 4 to 48 MHz oscillator, HSE. In STM32C071 microcontrollers, an additional 48 MHz oscillator, called HSI USB 48, is available for USB crystal-less application. The system clock, called SysCLK, can be derived from HSI USB 48. The AHB clock, called HCLK, is obtained by dividing the system clock by a programmable prescaler. The APB clock, called PCLK, is generated by dividing the AHB clock by programmable prescalers. The RTC clock is generated by the low-speed external 32.768 kHz oscillator, LSE, the low-speed internal 32 kHz RC oscillator, LSI, or the HSE divided by 32. The LSE can remain enabled in all low-power modes except shutdown. The LSI can remain enabled in all modes except shutdown and standby. Each oscillator can be switched on or off independently when it is not used to optimize power consumption. The HSI48 is a high-speed internal 48 MHz RC oscillator with 1% accuracy and fast wake-up times. It is trimmed during production and can be user-trimmed for higher precision. The HSI48 can serve as the clock source when waking up from stop mode and acts as a backup clock if the HSE fails, as detected by the clock security system. The HSI48 automatically wakes up from stop mode to be available for peripherals that need it, even when it is not the system clock. Additionally, peripherals like USART1, USART2, and I2C1 can activate the HSI48, while the MCU is in stop mode if HSI48 is set as their clock source. This table provides the characteristics of the HSI48 clock. The HSI48 accuracy can be improved by implementing a trimming procedure based on TIM14, TIM16, and TIM17, Channel 1 input capture. A clock reference such as HSE divided by 32 or LSE is used for high accuracy capture of the current value of the counter clocked by HSI48. The HSI clock has a typical 1.4 microsecond startup time, while the HSE clock has a typical 2 millisecond startup time. Available on the STM32C071 devices only, the HSI USB 48 clock signal is generated from an internal 48 MHz RC oscillator. It can be used as clock source for the USB peripheral or system clock. The HSI USB 48 is trimmed during production tests and can be user-trimmed with a small linear scale step. The HSI USB 48 clock is of high precision thanks to the clock recovery system or CRS. The CRS uses the USB starter frame signal, the LSE clock, or an external signal as timing reference, to precisely adjust the HSI USB 48RC oscillator frequency. When the CRS is not used, the HSI USB 48RC oscillator runs on its free run frequency that is subject to manufacturing process variations. The devices are factory calibrated for about 3% accuracy at an ambient temperature of 25 degrees Celsius. This table outlines the characteristics of the HSI USB 48 clock. Its accuracy can be enhanced using CRS, with a small trimming step size of 0.11%. The high-speed external oscillator, or HSE, ensures a reliable crystal system clock. It supports 4 to 48 MHz crystals or ceramic resonators, as well as an external clock source in bypass mode. The clock security system, or CSS, can automatically detect HSE failures. If a failure is detected, a non-maskable interrupt is generated, and a break input is sent to timers to safely shut down critical systems like motor control. If the HSE fails, the system clock switches to the internal HSI 48 oscillator to prevent application disruption. In external source mode, also called HSE bypass mode, an external clock source must be provided. It can have a frequency of up to 48 MHz. The external clock signal, that can be a square, a sinus, or a triangle, must drive the OSC in pin. The OSC out pin can be used as GPIO, or it can be configured as an OSC EN alternate function to provide a signal enabling the stop of the external clock synthesizer when the device enters low power modes. STM32C0 devices feature an ultra-low power 32 kHz RC oscillator LSI, available in all modes except shutdown. The LSI can clock the RTC and the independent watchdog. It has an accuracy of plus or minus 1.5% across temperature variations and plus or minus 0.1% to 0.2% over voltage fluctuations. The LSI typically consumes 110 nanoamperes. If the independent watchdog, IWDG, is activated, the LSI oscillator is forced on and cannot be disabled. The 32.768 kHz low-speed external oscillator, LSE, can be used with an external crystal, resonator, or clock source in bypass mode. In bypass mode, an external clock source of up to 1 MHz is required. The oscillator's driving strength is programmable and can be adjusted at runtime via the LSE DRV bit in the RCC Control Status Register 1, RCCCSR1, to balance robustness, startup time, and power consumption. The clock security system monitors the LSE for failures. If a failure occurs, the system switches the RTC clock to the LSI and automatically generates a non-maskable interrupt. The CSS is functional in all modes except shutdown and remains active during reset. The LSE can also be used as the source clock for sys-CLK. STM32C0 introduces pin sharing between high-speed and low-speed oscillators, providing flexibility, particularly in low pin count devices. For example, PC14-OSCX in and PC15-OSCX out are shared by both LSE and HSE, meaning these clock sources cannot be used simultaneously. The system clock is selected among the LSI, LSE, HSI USB 48, HSI 48, and HSE clock sources. The maximum system clock frequency is 48 MHz. The APB bus frequencies are up to 48 MHz. Upon system reset, the HSI sys clock derived from HSI 48 oscillator is selected as system clock. When a clock source is used as a system clock, it is not possible to stop it. Various clocks can be output on I/O pins. The MCO and MCO2 pins can independently output clocks selected from LSI, LSE, SYS CLK, HSI USB 48, HSI 48, or HSE. These clocks can be further divided using programmable ratios. The LSCO pin is dedicated to low-speed clock outputs, such as LSI or LSE, and can be active in stop mode. Dynamic power consumption can be optimized by gating peripheral clocks. Each peripheral clock can be enabled or disabled in run and low-power run modes. By default, peripheral clocks are disabled except for the flash memory clock. If a peripheral's clock is disabled, its registers cannot be accessed. Additional registers control the peripheral's clock during stop and sleep modes, including peripherals with independent clocks that remain active in stop mode. These control bits have no effect if the peripheral's clock enable is cleared. To reduce power consumption, clocks should be disabled for unused peripherals. This slide lists RCC-related interrupts. Both the LSE and HSE clock security systems, as well as all oscillator-ready signals, can trigger an interrupt. The flag indicating an automatic clock switch due to LSE or HSE loss must be cleared in the NMI interrupt service routine. The RCC unit in the STM32C0 is similar to that of the STM32G0, but introduces several new features compared to the STM32F0 series. The NRST pin has 3 possible configurations. Reset input, which allows external logic to signal a reset. Reset input and output, or legacy mode, where any valid reset signal on the pin is propagated internally, and all internal resets are driven to the pin. And GPIO mode, where the pin functions as a standard GPIO, and resets are managed solely by internal sources. The reset holder feature can be enabled in the option bytes to keep the pin pulled low until the voltage meets the VIL threshold. The system operates without a PLL for cost efficiency, relying on the HSI 48 oscillator for the maximum 48 MHz speed. The clock security system monitors the LSE and will automatically switch the system clock to LSI if an LSE failure is detected. Regarding STM32C0, the timer clock TIM PCLK runs at the PCLK frequency if the APB prescaler division factor is set to 1, or twice the PCLK frequency otherwise, meaning timers can reach the system clock's maximum frequency. HSI USB 48 is a new feature offered by STM32C0. In addition to this training, you may find the power control and interrupt controller presentations helpful. For more information, refer to Application Note AN 2867, which is an oscillator design guide for STM8S, STM8A, and STM32 microcontrollers. Thank you for attending this presentation.